Okay, video part 2 for subchapter 4.4 energy in reactions. Now in this video I would like to talk about thermochemical equations, something like that. In the last video we have established, hopefully, that just going back one slide, that when delta H value, the change in molar enthalpy, is larger than 0, positive value, it's an endothermic reaction, and if delta H is less than 0 or negative value, it shows the reaction is exothermic reaction. Now in that slide there were two equations, but yeah, that is actually what's known as thermochemical equations. Here's another example. Magnesium carbonate, which is solid, is added to hydrochloric acid solution, and if you let them react, magnesium chloride, water, and carbon dioxide will be produced, and that's accompanied by delta H value that says 90.4 with negative sign on it. That also shows that the heat has been released from this reaction. Thermochemical equations indicate the mole ratio of reactants. Now the equation itself needs to be balanced. The number of moles of each substance in a species, they need to be balanced, and the state of each reactant and the product need to be shown. The quality of heat energy released or absorbed by the mole quantities of reactants or products that indicates in the equation. So you need to show a positive and negative sign, and also delta H value, including delta H value. That's thermochemical equations. I just would like to point out on the mole quantities part. Now that delta H value is in kilojoules per mole, not only just kilojoules. That shows that per 1 mole of magnesium carbonate solid, 90.4 kilojoules would be produced. So it needs to be per mole of the reactant here. So again, let's see what you have noticed from this equation. When blah blah of blah blah magnesium carbonate reacts with da 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 of da 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 da, that was 1 mole of solid magnesium carbonate reacts with, follow the pattern there, 2 moles of aqueous hydrochloric acid because of the solution. What is produced? If you follow the pattern, hopefully you can see blah blah of blah blah water formed, 1 mole of liquid water is formed, and then blah blah of heat energy is blah the surroundings. What do you think? Well, 90.4 kilojoules of heat energy is released because it's negative. In this case, surrounding consists mainly of the solution in which the reaction occurs. So it's water that's present or being created as the reaction goes. The temperature of the solution, what do you think? Well, it's an exothermic, so it should increase. Another way of writing thermochemical equations with an added heat term. So instead of having delta H value outside of an equation, you could write KBr03 solid plus 42 kilojoules. So you're adding heat there, then you can make KBr03 into solution. Or you could be getting heat out, and you can include that in your thermochemical equation. So 2 mg plus O2, so you're burning magnesium, and that releases energy, a lot of them, 1200 kilojoules, and to magnesium oxide. Sorry. And we know that that's an exothermic heat and light is produced. Oops, not that. Let's see other examples of thermochemical equation. So, complete combustion of 1.00 mole of propane produces at 2,200 kilojoules of heat. So if you are to write this, well, let's start with propane. So C3H times 2 plus 2, 8 plus O2, that forms CO2 plus H2O. Now that would be just a normal chemical equation that's even not balanced. You must include states first. Propane is gas, oxygen is gas, CO2 is gas, water will be pure liquid. Yeah, it's not balanced, so let's balance that. So C3H8, well, if you follow Mr. Cho, CHO in the order, you'll be balancing C first, and there are 3 of them, so I'll put 3 here. There are 8 hydrogen on this side, so I'll put 4 times 2, so that should make 8 there. Oxygen wise, there are 4 atoms plus 3 times 2, that's 6 atoms, so 4 plus 6, that will be 12, no, 4 plus 6, that's 10. Therefore, if you divide by 2, 5 of them is required. Now that's probably just half of it. The most important information you have to add is this. Now, because this is a combustion reaction, heat is differently produced. So don't forget the sign, negative 2, 2, 0, 0 kilojoules per mole. All that is the thermochemical equation. All right, let's look at ethane's example here. You'll be doing basically the same, but there is one twist to it. Ethane has got 2 carbons in it, so times 2, but in the other 2, we should have 6 H's plus oxygen. Let's just start adding states as well as we go. Okay. Now, how many carbons? There are 2 of them, so well, let's balance it like so. And H next. There's one tip that I should give you. If you are normally balancing a complete combustion reaction, and if you have even number for hydrocarbon, just don't think anything, just add 2 to start with. So 4 carbons would have been there, and 2 times 6, so that should be 12 in total over here. So 6 times 2, so that's 12. 6 oxygen plus 8 of the oxygen atoms, or if you are just bundling with O2s, that will be 4 here and 3 here. So that would be 7 O2. Now if it's a normal equation, that would be correct. But because we are looking at 1 mole of heat, because that heat produced is actually in kilojoules per mole. This is not per mole. So you now have to have everything here. So what's correct would be just 1 of that, C2H6 gas, plus, now 7. You have to have it. The thermochemical equation is the only equation that you can do this. O2 gas. So 7 over 2. And then 4, no, sorry, you are dividing by 2, aren't we? 2 CO2 plus 3 H2O liquid. Now, that's not the end as well. Hopefully you can see this corner. You actually have to have delta H equals to negative, because heat is released 1557 so that would be the whole complete thermochemical equation for ethane's complete combustion.